So today I'm doing some practice on chapter 15, which is on thermodynamics. And namely, I will start with a focus on practice on entropy. And afterwards, I'm going to solve some general questions on thermodynamics. So I remind you, the change in entropy was defined previously as delta S equals the integral of dq over T. And if the temperature is constant, then we can write delta S to be whatever Q was added to the system or removed from it divided by the temperature. We might be interested in delta S for the system or delta S change in the surrounding. We name this delta S of the universe. When we study delta S of the universe, this would be, in that case, would be studying what changed in the system and the surrounding as well. One important remark is that for the system, the entropy change is going to depend, as we said before, like this is a state function. So it depends only on the initial and final states. So for the system, I will just check the final state of the system and the initial state of the system. And one important thing is that if the system is going through a cyclic process, then delta S is going to be essentially zero because the initial and final states are the same. For the universe, this is not necessarily the case. We're going to have to see what happened in the reservoirs, namely, plus what happened to the system itself. If the system is in a cyclic process, then the change of entropy is essentially zero, and then you check just what happens to the reservoir. So I'll just name this for a cycle, and this is going to be equal to what changed in the reservoirs only. And for the reservoirs, you're going to check how much you removed from a hot reservoir and how much you removed from a cold reservoir per se. So this is basically how you study entropy changes if you have a certain system with some surrounding around it. If I don't have a cycle, you will have to check what changed in the reservoir and what changed in the system itself, and this would give you delta S of the universe. We're gonna see more of that later on, but for now, I'm just gonna be using the basic formula, delta S. Yeah?
بس سؤال, could you repeat what the formula for delta S cycle is?
Yeah. So I was first saying that when I check the change in the entropy, by the way, I remind you, for those of you who are still finding entropy confusing, first, I want you to know that it's normal for entropy to be a very confusing concept. As a matter of fact, like understanding it till now, even by advanced physics students, you might find them that they are not very skillful in describing what it is. And to you as well, because it's a description of how disordered things are, which is like a description of chaos, which is not very simple to study. And specifically when we started with the statistical part at the end of the chapter, you saw how confusing that is. Like I'm checking how many arrangements of randomness I could have, and that's what entropy basically is, which is not simple. And you would see how it's showing us how the universe favors disorder over order, simply because there's one arrangement to get an ordered system and infinite arrangements. Not infinite, but depending on the number of molecules, it could go to a really large value for arrangements of incorrect order or disorder. And that's why delta S is always increasing, or zero in case we get back to that ordered arrangement. So the concept itself is just a description of disorder A more physical way of describing entropy is saying it's a description of energy dispersion, or how energy is lost from the system to the surrounding, leading to having this irreversible process. So, okay, the physics description itself is not very straightforward to understand, but for now you have an idea. And the formula itself depends on the amount of heat and the temperature of the system. And the formula is basically telling me whenever you are adding heat, the entropy is going to be increasing, namely because giving more energy increases the randomness. Imagine you have a solid and you're adding more heat until it becomes in the gaseous phase. The gas is going to be in a much more random motion than the solid state where you had at least some ordered atoms. So the entropy of a solid is essentially smaller than the entropy of a gas. So, and you can think about it in terms of randomness as well, or disorder. Yeah, so whenever you're adding heat, you will expect that delta S is going to be positive. If you're removing heat, then you will essentially substitute Q to be negative, and you will obtain delta S, which is negative. Yeah, and then just be aware that sometimes I would ask you to find delta S of the system we are studying itself. So for example, I have the system, remember, it's like some substance we are studying. It could be a gas in a container with some piston. This is the system. And as it expands or compresses, sometimes some loss of energy occurs to the surrounding. This is the surrounding, which might contain some air, for instance. Sometimes the surrounding is not just this atmosphere around the system. No, I have a more sophisticated case. Sometimes the surrounding is a hot reservoir that is below the system. This is a surrounding. It's going to be giving in heat, for example, into the system. So you might be asked to find the change in entropy in the surrounding, for example, and then you would check how much the hot reservoir has given heat to the system, and its delta S will be whatever heat it gave divided by the temperature. And you would substitute this as a negative value because it's a lost energy for the hot reservoir. But if you're checking the system itself, it will be receiving some heat. So its entropy is going to be positive, whereas this one is going to be negative. And if you add both of these, and let's say there was no friction, so there's no other surrounding taking any energy, you would end up with delta S to be equal to 0. So if I have no friction, delta S of the universe is equal to delta S of a reversible process. And this is going to be 0. And it makes sense if you check the calculations I have here. It's going to be delta S of the surrounding plus that of the system. And you can see how this was Q given over T plus Q taken over T, which is going to be minus Q over T plus Q over T, which is 0 again. You can see how I got back to a 0 for my answer, right? Because whatever the hot reservoir has given to the system has taken it. So it's equal amounts of heat if I'm considering no heat dispersion, no heat loss, and no frictional forces. So there's nothing given to the surrounding except what the hot reservoir has given to the system. Does this make sense?
Professor, the reservoir is the same as the surrounding?
The reservoir is part of the surrounding. Look, as we said at the beginning of the chapter, I told you, when we study processes, thermodynamic processes, I have to identify my system. It is the substance that is undergoing a process. What is undergoing a process here? The gas in this container. Do you agree?
Yes.
This is my system. Anything around it, as we said in the first slides, is a surrounding. So anything outside the system is a surrounding. So the hot reservoir is a surrounding. The air around the system is a surrounding, right?
Okay.
And we discussed previously different types of systems according to their interaction with the surrounding, right? We said we have a closed system, an isolated system, and an open
Open
system.
system.
What's the case we have here with the hot reservoir?
It's an open system.
No, it's not.
With a hot reservoir it's only closed لأنه في energy transfer بس
Exactly.
mass transfer.
It's not isolated because heat is entering the system, and it's not open because we have this piston. No material is leaving from the container. So this is a closed system, if I would like to identify that. All right, any questions here so far on the concepts? You might find them confusing, again, still, but as we do the practice, you will get used to it. All right.
Professor, بالفورمولا تبع delta S universe cycle, what's the subscript of the first delta S?
Reservoirs? Is it?
delta S plus delta
Here?
SH السطر اللي تحت.
Okay, yeah. Let me see. So I wrote, I forgot what I was talking about here. So I said it's delta S of the reservoirs. I was considering two reservoirs, for example, because usually we have a hot and cold reservoir if it's an engine per se, right?
Yes. Okay.
Yeah, so I said if I have two reservoirs and a system, okay, then you would consider the cold and hot reservoirs to find the change in entropy for the universe.
Okay, thank you.
Okay, other questions? The rest of you, do you have any questions? All right. Okay, so let's at least just start with a problem. Find the change in entropy of the hydrogen molecules when 3 kilograms of ice melts into water at 273 K and 3 kilograms of water changes into steam at 373 K. So we have some phase changes in these two cases. I'll just start with the general formula. So one super privileged thing about phase change is that the temperature is constant. So I can simply write delta S to be whatever Q I'm adding or removing divided by the constant temperature of the system. So, and for the phase change, Q is simply equal to ml. I'm given the latent heat of fusion and the latent heat of vaporization. So I'll just substitute basically for the first part. I have some melting ice. I have 3 kilograms, namely, and I will use the latent heat of fusion and divide by the temperature, which is 273 kelvins. And you can find the change in the entropy. So I'm checking the entropy of the hydrogen molecules. Am I adding or removing heat in this case? I'd like to see if the entropy should be increasing or decreasing in this situation. Is it positive or negative? Is ML plus or minus?
Positive, we're adding heat to that.
Exactly. We're melting ice, so we're essentially heating ice up. So we're adding heat. I'm interested in the entropy of the water itself, the system itself, to which I am adding heat. So this should be positive. I might ask you find the change in entropy of the surrounding. And then there must be some hot reservoir heating up the water molecules and giving out some energy. And then you put delta S for that to be negative. So here I can just write down the final answer plus 3.68 times 10 power 3 joules per Kelvin. Any questions? Quite straightforward, quite simple to study. You will see that most of our studies are just very simple, except for the tiny tricks of the signs and whether we are studying the system or the surrounding or the universe. But the calculation itself is always quite short with entropies. Part B, water is changing to steam at 373 K, which is 100 degrees Celsius, right? Boiling point of water. So delta S is, again, ml, but now that's for vaporization rather than that of melting, divided by T. So I have 3 kilograms of water, and the latent heat is given to us, 2.26 times 10 power 6, divided by the temperature, which is 373. So again, when I am vaporizing the water, I'm adding heat to the water. So the water itself experiences a positive change in the entropy. So an increase in entropy, right? So this gives me, the final answer is 1.82 times 10 power 4. And again, this is joules per Kelvin. Yeah?
You are adding heat to the delta S would be positive. If you are removing heat, it would be negative.
Of course, yeah, true. Now, I want to comment on this because this is a source of confusion for some students. How come that delta S is negative when I explicitly express to you by the second law of thermodynamics that delta S can never be negative?
Because this order would be increasing in the surroundings, so it's decreasing in the system, but increasing around.
So the second law actually expresses delta S of the universe to be always positive or equal to 0. Not that of a system, not that of part of a process, because certain processes will definitely have some negative change in the entropy. So basically, the second law tells me that the change of entropy of the universe is always positive or equal to 0. Part C says, on the basis of the answers, discuss which change creates more disorder in the collection of H2O molecules. So essentially, the one that has more change in entropy is going to have more disorder, right? You can see how part B, delta S of part B, is greater than delta S of part A, which means that more disorder happens in vaporization. Does this make sense? When we go from ice to water, I am increasing the randomness, that's for sure, because water molecules are more flexible to move than ice water, which is fixed and vibrating in place and not even moving. For the gaseous phase, things become even more random. So this is liquid water, of course. In both cases, the randomness increases. But the thing is, when we go from water to gas or from liquid to gaseous state, whatever the substance is, the amount of randomness increases way more than when you go from ice to water. Why? Because in a vapor, the distances between the atoms are way more. The motion is way more random. The molecules are filling up the whole container. So there is way more disorder occurring. And you can see that verified mathematically when we calculated the entropy. When we were melting, delta S was of order of magnitude of 10 power 3. You can see that in the answer here. Whereas in part B, delta S was an order of magnitude of 10 power 4. So the randomness is 10 times more than in melting. Vaporization makes more disorder than melting. Any questions? So in this question, this is an application of engines and pumps, which are basically at the heart of our definition of entropy. But in the calculations, they're quite unrelated. You don't see the expression of the entropy explicitly there, but we make use of the fact that the entropy of the universe is always increasing and use that in engines, as a matter of fact. So I'm studying here a Carnot refrigerator. Remember, we said in engines, we are making use of the flow of heat from some hot reservoir, expanding a substance inside the engine, making some work as it expands, and then releasing some heat as it compresses and does even more work. This is how engines operate. Whereas in pumps or refrigerators, we are doing the opposite. We're doing work to take heat from the cold compartment and push it towards the hot end, which is the non-spontaneous direction of energy transfer. So what we're considering now is a refrigerator. So it's basically a pump. Remember, the difference between the two is basically it would reflect in the efficiency per se. So I have the efficiency is going to be equal to, in engines, my output is the work, my input is QH. And the work done, we defined it as QH minus QC from conservation of energy. And we said if I have a Carnot engine, then the efficiency can be written in terms of the temperatures only. This is an idealized engine, and basically Carnot designed it in order to just know what the limit of the efficiency is. By the way, Carnot was a French scientist, and he even served in Napoleon's army in wars. At some point when Napoleon's downfall occurred, he wanted to just serve the country somehow. And he found that, and then the discovery of the steam engine occurred. And different countries in Europe started making steam engines, and it was like part of the beginning of the Industrial Revolution. But back then, the first steam engines, they had an efficiency of 2%. Imagine that. So you would be burning 100 kilograms of coal, and only 2 kilograms of these are contributing to the motion that the engine is making. The rest was all wasted heat. So Carnot wanted to see how can we improve this efficiency? And by that, he thought that he would like give France some privilege to make better engines compared to other countries. And at some point, he was able to at least know what an ideal engine would have in terms of efficiency and what we can reduce in order to reach that ideal efficiency at least. And yes, he discovered that the Carnot engine, or his ideal engine, would have an efficiency dependent only on temperatures, whereas any other heat losses from friction and other stuff are removed. And it would never really get to a value of 1 because the temperature of the cold reservoir is always taking some heat. And that actually contributes to the work as well, which we can't remove unless we were able to have some cold reservoir of temperature equal to absolute 0. And by the way, his discovery was the step towards discovering the absolute 0 and the Kelvin scale. Lord Kelvin discovered the Kelvin scale based on Carnot's discovery of this efficiency formula, because he knew that there would be some 0 temperature here, and he substituted for the hot temperature and discovered the Kelvin scale accordingly, and found its relationship with the degree Celsius scale. For the pump, the efficiency would be dependent on our output, which in this case is QC, and the input is the work that we are giving to the pump. The work is basically based on some electric energy that we are getting for our refrigerator, for instance. And again, we can write W to be equal to QH minus QC and rearrange our equation. Sometimes the equation is written as, if we divide by QC in the numerator, we would get QH over QC minus 1. And again, we can have a Carnot pump or refrigerator where the efficiency depends only on the temperature difference. And then we would have this formula. Any questions on these? Of course, we did something, which is that we didn't name this efficiency, rather we named it the coefficient of performance, namely because it's not really an efficiency. And it's also never written in percentage as we do in efficiency. And also its value can be greater than 1 because the QC itself is contributing to adding to QH. So mathematically speaking, this is going to be greater than 1. All right, so let's see what the question is. We have a Carnot refrigerator transferring heat from its inside to the room air outside. Part A, find the coefficient of performance of the refrigerator. Since this is a Carnot refrigerator, so I can write the formula of that for the Carnot fridge, which is only in terms of temperatures. So this gives me 1 over 20 over 6 minus 1. One mistake that could happen here is what? What's a mistake I have here?
Not changing to Kelvin.
Exactly. And I'm gonna leave this in the solution for you to always see that. +20 plus 273 over 6 plus 273 minus 1. So I will calculate this. You will get 20. This is the unit of the coefficient of performance for this refrigerator. Part B, find the magnitude of the minimum work needed to cool 5 kilograms of water from 20 to 6 degrees Celsius when placed in this refrigerator. So we want to find the work needed.
It's Q over coefficient of performance.
So I know that the COP, I have defined it as QC over W. I can write W to be QC over the COP. All right, I know this is 20, which is good. So I'll need to see how much heat I have taken from the cold compartment in order to cool this substance. Now, the amount of heat that we are going to be removing is going to be equal to MC delta T because I'm cooling water from 20 to 6. I will, of course, use the specific heat of water for 186. And delta T is 20 minus 6. This I can leave in Kelvin because I'm checking for delta T. And you can find now the value of W by just substituting and calculating. You will get 15,000 joules. Any questions? Okay, so when we speak of the COP, this is the case where we are doing work to obtain some heat exchange in the non-spontaneous direction. Namely, in the refrigerator, for instance, I was trying to remove heat from a compartment, the compartment of the refrigerator, to the outer atmosphere or to the outer surrounding. And in that case, my output would be whatever I removed from the refrigerator, which is QC, over my input, which is W. This is the COP formula. Now, for the AC, I am removing heat from the room to the outer surrounding, which is the outdoors. The outdoors is at a higher temperature, so I'm removing a QC and throwing it in QH, right? I'm doing work to take QC from the interior of the colder room to the outside. So again, my outcome is to remove QC. So the COP will still be QC, and the input is W, because I'm doing work with the AC to remove QC. Makes sense? Now, the heat pump is a different story. The heat pump is an electric appliance in your home. What it does is that it's basically the AC operating in the heating mode. So لما تستعملوا ال AC بالشتاء عم تعملوا heat pumping. What you do is you take heat from the outside and push it to the inside. Now, outside, you have a colder environment, and inside, you have the warm room. In the outdoors, you have, let's say, minus 10 degrees Celsius. It's winter, it's cold. Your room inside, let's say it's at 10 degrees Celsius, and you want to warm it to the regular nice 25 or 22. So what you would be doing is the heat pump removes heat. We do work on it. We give it some electric energy to remove some heat from the outdoors into the room to warm up the room. What I want is to add heat to the room. This is my output. So what we want equals my output. In this case, it is adding heat to the room. And this is basically adding some QH. This is my output. What we give is basically some electricity here, doing some work. And this is my input. And the COP and the efficiency as well are both the output over the input. So in this case, for the heat pump, it's going to be QH over W. Now, several textbooks and myself, we like to name all of these three, we name them pumps versus engines, like as compared to engines. In engines, we speak of efficiency. In pumps, we speak of the COP. In engines, the efficiency is always the work divided by QH. In pumps, I have to distinguish between the case where I'm cooling down a compartment or heating up a compartment by doing work. We're heating up a compartment by taking some heat from a colder surrounding. Makes sense?
Yes, thank you.
Okay, so let's see what we have here. A Carnot engine operating between two heat reservoirs at temperatures TH equal 500 and TC equals 300. The engine absorbs QH equals 600 joules of heat from the hot reservoir. Calculate the total entropy change of the universe as a result of this process. So I want delta S of the universe. Like I told you, this is going to be equal to delta S of the system plus delta S of the surrounding. Now, one thing I know is that in engines, we have cycles. So delta S
is 0.
is 0 for the system. All right. What remains is delta S of the surrounding. So how do we find that? In the surrounding, around the engine, I have a hot and cold reservoir, right? Namely, the hot reservoir is giving the QH, and the cold reservoir is giving the QC. So I write this as delta S from the hot reservoir plus delta S from the cold reservoir. Now, because this is a Carnot engine, then I don't have any frictional forces. So I will assume the change in entropy is just due to the hot and cold reservoirs. Nothing else going to the surrounding other than these two. What these two are doing is the surrounding effect only. So, okay, I will write these as QH over TH plus Q cold over T cold. Do you all agree?
So why did we write the delta S surrounding is delta SH plus delta SC?
Yeah. What is surrounding the engine substance? So remember, in an engine, we drew it in the previous page. In the engine, I am allowing some heat to flow into the system. The system expands, it does work. And then the system compresses and releases QC. Do you agree?
Yes.
And the system undergoes 4 processes, let's say, sometimes 3 processes, by the way. The engine doesn't have to be going through 4 explicitly, but it's a Carnot engine here. So it's essentially 4 processes, 2 isothermal, 2 adiabatic, but it's a cycle, so the system itself does not undergo any change in entropy. So this one goes to 0. Now for the surrounding, what is surrounding the engine substance? This is the engine substance here. It was the thing expanding and compressing as we add and remove heat. What's surrounding it is whatever is out here. When I added QH to this engine, it was from the surrounding. When QC went out from the system, this is towards the surrounding as well. Does this make sense?
Yes.
Now, if this was not an ideal engine, then you would also have to account for some friction loss and heat loss and diffusion of heat to the outside, similar to a cup of coffee that is cooling down and its heat is all going to the surrounding. But I have a Carnot engine, which is an ideal engine, and the only exchange is only from QC and QH. Nothing else is being exchanged with the surrounding. So the surrounding will be essentially only what I added as QH and what I removed as QC.
But didn't we take QH from the surroundings and add QC?
True.
So why do we say plus delta SH, not minus?
Ah, yeah, I will actually put a minus sign. You're right. Yeah, I didn't do it yet because I wanted to write the expressions of the Qs and then deduce like what has entered the surrounding and what has left it to put some signs. Definitely there will be some opposite signs.
Okay, thank you.
Okay, so let's take a look at the values of the heats involved here. I am told that the engine absorbs QH equals 600 joules of heat from the surrounding. So I know QH is 600. I also have TH 500, TC 300. I don't have QC, which is a bit tricky to think of.
Can't
Also,
we get the efficiency and then
excellent.
have
Yeah,
QH?
that's correct. So what I will do is I will write down the efficiency formula. The efficiency, its general formula is 1 minus QC over QH. But for a Carnot engine, it can also be written as 1 minus TC over TH, which tells me that QC over QH equals TC over TH. And then I can also calculate QC because I have everything else. Okay, so you can see how I have everything here and I can calculate QC. This will be QH TC over TH. So this is 600 times 300 over 500. You will get 360 joules. All right, so I got 360 here. One thing is I need to just be careful which heat is negative, which is positive, if any. The surrounding is giving out which heat, QH or QC?
QC.
So I have this engine. I give it an input. What was my input to the engine? Remember the input, it was QH. Yes, the heat that we added, which is QH. Remember, this is the input. This was what my output. But what I'm thinking of is whether QH is an added or removed heat from the surrounding. Since this is an input to the engine from the surrounding.
It's removed from the surrounding.
So it's removed, so it's negative. Now, you calculate this, and you would be shocked that you get 0. You go back to the options, and you find indeed there is a 0. And then it occurs to you that this is a Carnot engine. It's a reversible process. And in reversible processes, we said delta S of the universe equals what? It's equal to 0. So we could have actually solved this whole thing with just noticing this fact. But I wanted to show you how the calculations match with predictions. Any questions? So in this question, I'm studying an ideal gas. So a system undergoes an isothermal expansion where the volume of an ideal gas changes from V1 equal to 2 liters to V2, which is equal to 8 liters at a temperature of 300 K. We want to find the change in entropy of the system. So one important thing to note about the situation of an ideal gas is that we can actually rearrange a formula for the change in entropy according to the values of Q. So one thing to notice is that we know that the general formula is delta S equals the integral of dq over t. Now, I gave you the formula of delta Q over T, which could work if I have a constant temperature. But in this case, we essentially don't have always constant temperature for gases. We will have a constant temperature only if I have an isothermal process. Otherwise, it's going to have to be this integral form. So what I have to do is I'm going to try to rearrange this equation. I will start by actually making use of the first law of thermodynamics, which says that Q equals U plus W, right? I will write this in terms of dq. Eventually, I'm going to have to actually integrate, which is not something very difficult because in this case, I have an easy integration to do. So I would write dq as du plus dw, and I will write down the general formulas. I know that U is NCV delta T for an ideal gas, which I can write as NCV dt, whereas for W, the general formula is PdV. Remember this from our first study of thermodynamics. So what I will do is I'm gonna try to integrate this. So delta S can be written as the integral of NCV dt plus the integral of PdV. One nice thing I notice is that NCV is constant for the same gas, so I can take that outside. And okay, I have to divide by T. Sorry about that, right? Because delta S is dq over T. So I divided by T, and I'll remain with a T in the denominator here. In my second integral, things are not as straightforward as the first term, namely because P can be changing and T can be changing, and the integral is over dV, which is even more annoying. So what I will do is I will use the ideal gas law in order to try to write P and T in terms of V. So if you rewrite P, for instance, as NR T over V. You will notice how T cancels out, and you would get NCV integral of dt over T plus, okay, NR is constant, I can take it outside, and here I will have dV over V. You can see what's the solution of these integrations. We can now solve the integrals because everything inside is like the same quantity, so we can integrate. So you can see how this will look like ln T final over T initial, if we are integrating from some initial to final temperature, and plus nr ln V final over V initial. This formula represents the change in entropy of an ideal gas for any process. And this is given to you in the exam. So this derivation is not required of you, namely because it contains integrations and you're not required to know integrals. So I'm gonna just keep this equation in front of me whenever I am told we are studying an ideal gas. Now, one nice thing about this formula is that, let's say I have an isochoric process, then this cancels out. What if I have an isothermal process? This cancels out. And if I have an isobaric process or an adiabatic process, both terms will stay there.
I'm sorry, it lagged for a minute. Just the thing about cancel which one when we have what.
شو قلتي هلا؟
Can you just repeat what you said just like 30 seconds ago, علاء عندي?
Yeah, I just said that let's say you have an isochoric process. I can actually write these down here. What do we know about an isochoric process? V initial equals V final. So actually, my formula for delta S, these terms will cancel out because V final equals V initial. So we have ln of 1, which is 0. Do you agree? So delta S will only contain the first term. It will be NCV ln T final over T initial. And I also said, what if I have an isothermal process? Then T initial equals T final, and delta S will be equal to, so the first term cancels out in that case. Now, if I have an adiabatic process or an isobaric process, then all of these terms will actually be there. Both terms will be there in the formula. So this can work for isobaric, adiabatic, and generic process. If I have a cyclic process, delta S is 0, right? Okay. All right, so here I have an isothermal expansion. Lucky me, I will cancel this out, and I will write delta S to be nr ln V final over V initial. We have the volume change, and we have the number of moles, and we have R, so all is quite straightforward here. V final is 8, V initial is 2, so you can calculate delta S. Let me see if I found the final answer. Yeah, you would get 11.53 joules per Kelvin. This is answer 1. Does it make sense for the entropy to be positive in this case? Well, we have some expansion, so V is increasing. So heat is added to the system. And we said when heat is added, then delta S is positive. Any questions?
Yeah.
So, Professor, when do we use the formula delta S is delta Q over T, and when do we use the one we just derived?
That's a very nice question. We use this everywhere in the world. This works anywhere for any question. This one is only for an ideal gas. Remember what we solved so far today. I considered an ice that was melting, so I put Q, which is ml. I considered water, which is vaporizing. Again, I put m times L. I considered some water that is cooling down in the refrigerator, so I put Q to be mc delta T. I considered an engine with some substance, God knows what it is, not necessarily an ideal gas. So I studied delta S to be Q over T, and I checked how much heat I added to the surrounding and removed from it. For the system itself, the engine itself, it was going through a cyclic process, so I said delta S is 0. For the surrounding, I was taking some QH, so I had QH over T. The surrounding or the reservoirs essentially have a constant temperature. That's why I used Q over T or delta Q over T. فيك تكتبيها هيك. And Q was the amount of heat, QH and QC. When did I use this one? When I was told I have an ideal gas. So yes, I can use this formula if I have an ideal gas. Now, if you were given an ideal gas in an engine, how much would delta S be?
0.
True, Majid?
Well, isn't it a cycle?
Yeah. So if I told you I have an ideal gas, so Hala here, I told you the ideal gas has this expression, right? What if I told you the ideal gas is an operating substance in an engine? What would be delta S? Okay, it follows this expression, but I already know it's going to be in a cycle, so yes, it's 0. It also has to satisfy this formula. So yeah, we use this formula only for an ideal gas.
Professor, what do you
Questions?
mean?
In an engine, both volume and temperature stays the same when it's in cycle.
No, no. For the engine, there's a cycle with several processes, at least 3 to 4 processes, or maybe 2 in some hypothetical situation. So you have more than one process, but because your initial and final states are the same, because you have a cycle in an engine. In an engine, you will always have some repeated cycle to do work. Because you have a cycle, you immediately know that delta S of the system, which is the engine in this case, or the working substance of the engine, is 0. You understand?
It's in cycle, so it always goes back to the initial temperature.
Yeah, and S is a state function. It depends only on initial and final points. The initial and final points are the same, so S is the same for both. So delta S is 0. Now, if you want to see it in terms of this equation here, you will do delta S of process 1, and then add to that delta S of process 2, if you have like the cycles of your engine. If you add all of these up, they will add up to 0. So بتشتغلي فيهم وحدة وحدة وبتحطي هيدي الفورمولا وحدة وحدة, and then they all cancel out because you have a cycle. Just as what happened when I studied the surrounding for the reversible process. وقعدت وحليتها mathematically, I checked it out, and then at the end of the day, they just simply canceled out because it's a reversible process. Here, same thing. You will find delta S for the adiabatic process, then the isothermal, then the adiabatic, then back to the isothermal. You add all of these together to find delta S of your system, and surprise, it becomes 0 because you have a cycle here. Your initial and final states are the same. So your entropy essentially has to stay constant, and delta S has to be 0.
Yeah, understood.
Selena, any questions? Is this clear?
I still have a question on the equation delta S is QC over TC minus QH over TH. We can always use it. But if we have an ideal gas, we'll use this equation that we just derived.
Okay. So be careful. I used delta S equals delta SH plus delta S cold. This was delta S of the surrounding. And it was for a, we had a reversible process. If you had to study the surrounding and you had some irreversible process, what should we do? We will have to add some effect of energy loss to the environment or friction or whatever. Now, if I'm studying the system, not the surrounding, if you have a cycle, this is going to be 0. If you have a system which is an ideal gas, then you use the above formula with Lens. So, انتبهي سلينا. The first comment is, what you said, delta SH plus delta SC, you can always use it if you are studying the surrounding and you have 2 reservoirs, a hot and a cold one, which is the case for the engine, for example. But in the lecture, we solved for a copper rod, which was taking some QH from a hot reservoir and putting it into a cold reservoir. And we were checking the change in entropy of the rod here. Essentially, I will check the heat coming from here and the heat coming from here. So in that case, you are taking QH itself and transferring it from one side to the other. So in both cases, راح تحطي QH anyway. Yeah. So what matters is you know how many reservoirs you have, for example. Do you have a cold reservoir and a hot one? Then yes, you have to check the entropy of both and account it for your surrounding. Your process is not reversible, then you have to check for losses. Now, in problems, ما راح أحط لكم the losses and ما بعطيكم friction and like tell you to find the entropy change for the friction. So mostly you will see the first equation. Yeah, that's possible. The third one, for sure. The one for the ideal gas, definitely. But just be aware of the terms. Sometimes I'm finding delta S of the system. Sometimes I'm finding delta S of the surrounding. So just be careful what you're finding. Here, I was checking the change in entropy of the system. So I used the equation for the ideal gas because my system was an ideal gas. But when I put delta SH and delta SC, I was studying the surrounding, which contained reservoirs operating on a system. Other questions?
So the one we wrote in the PowerPoint, QC over TC minus QH over TH, is only for reversible engine?
Pay attention for the reversible engine. It's even simpler than that. If you're studying the engine itself, it has to be 0. And the surrounding as well. Like we worked on QC over TC and QH over TH, and we did some calculations. But then if it's a reversible engine, these calculations should give you 0. Makes sense?
Yes, thank you.
All right. So I'm gonna stop here for today. I think I should hold one more session as a revision for the exam. So we'll arrange for that. I think I'm gonna keep it in the afternoon, but we can talk about it if you have other suggestions. So if you have no questions, you can leave the meeting and have a good weekend.
Thank you, Professor. Have a nice weekend.
Professor,
Thank you.